Okay, it is time to get started. I do not see Maggie, nor Tioni, nor Satish or Holly. I know where Satish is. Okay, we're not going to do a Flip Friday today because my son hurt his finger, got stuck in the pocket of a guy's shorts playing flag football on Tuesday, and he still can't move that end of his finger. And so I think he probably ruptured a tendon just like I did playing flag football. And so the only time we could schedule for him to see the orthopedist is Monday at 1:30. And so we'll do the Flip Friday thing then, except for the problem, oops, I marked Maggie off instead of Holly. Holly and Tioni showed up. Yes. And Holly's making new friends. Sorry, Cody, apparently you're not cutting it. So I'm going to lecture today, and actually a lot of the stuff I'm lecturing on is relevant to the worksheet that you were working on for the Flip Friday.
Can we keep it, right?
Yeah.
Thank you. Thank you so much.
So, let us get started. So we're going to be talking about light and what we learned from light. And we're going to have sweet demonstrations. I think they're sweet. First, starting with a clicker question where I'm going to record your first answer this time.
Oh, no. I don't have it.
No, life will go on.
Whatever.
Excuse me.
Serious? Ah!
You forget it?
My slave. How many points am I losing at?
I don't know. I really don't know, so I can't.
Can I write it down and tell you?
Hmm?
Oh, yeah. Yes.
No, because I.
My life is
Do you have your clicker? Yeah.
I just had to switch to the Laurentian.
No, I was talking to Tioni, but then I realized, no, I need to update his number. That's the problem. Okay. Yep, everybody's answered. And everybody said the right answer without me having to say, okay, now everybody answer B correctly like I did last time when I started with the wrong one. Okay, so moving forward from that, we've already looked at this slide. The brief history of the models of matter, going from Democritus just saying that you have smallest pieces to J.J. Thomson with the recognition of electrons being part of matter and thus saying that you must have this mush with the general positive charge and then small points with negative charge, the electrons. Rutherford with his gold film, and actually it was Marsden who did the experiment, saying, no, that can't be right. We must have a planetary model where we have electrons orbiting the nucleus in circular orbits. Then Bohr, who came and worked with Rutherford and said, look, we know that isn't right, made the assumption of quantized angular momentum. Remember the angular momentum? We had Satish up here rotating around. And the angular momentum was the mass times radius times velocity. And Bohr said that angular momentum must be quantized, and turned out if they're doing circular orbits with quantized angular momenta, then they would also have quantized. That quantized means only discrete values possible. That actually goes to the question on why we can't have something coming to rest. It's those discrete values, and 0 is not one of the discrete values for motion of something that is bound. And so Bohr had this quantum idea, still circular orbits, but now quantized energies. And then we have our particle theory, or our standard model, the current understanding of an atom. And the current understanding says it's quantized. You have certain energy levels, certain angular momenta, certain blah, blah, blah. But we simply cannot say anything about the actual path an electron takes or where it is. We can only say the electron is likely to be found in this region. So when you see something and it shows like an electron going in a circle, It's actually not an electron going in a circle. It's saying the electron is most likely to be found somewhere within this circle. That's what that actually means. When I was in high school chemistry, I thought it meant that the electrons are doing these circles. And that is not our understanding anymore. So that's a quick rundown on the models. We saw this picture. This is the last one that we talked about. We have the different energy levels. And as God's my witness, I thought I had replaced that with a different slide. I start to worry about going crazy because I was pretty sure I'd replace it. It must be coming up where I replaced it. Anyway, moving on. When we talk about atoms, everything is made up of atoms. You, me, the world, everything we know is made up of atoms. Although, when we get late in this class, not today, but in this semester, we will discover that scientists have determined, astronomers have determined, that we only have any knowledge about 4% of the universe. So all of our knowledge, we say everything's made up of atoms. The stuff we know about the atoms that makes up everything is only 4% of the universe. We have no idea what the rest of the universe is. So, yeah. So while we might think we know a lot about physics and astronomy and whatnot, in the end we're like, wow, we are really, really quite ignorant.
Job security for scientists.
Yeah. Don't let us... Okay. The elements, the things that stuff is made up, are organized on a table that you see on the back wall. On that table, the atoms, if you go from left to right, you're going to more massive atoms. If you stay on the same line, the vertical columns were devised by Mendeleev to describe similar chemical properties. So if you look there, the top left is H for hydrogen. You go down below and you have Li for lithium, below that Na for sodium, below that K for potassium, Rb for rubidium, Cs, cesium, Fr, francium. All of those have similar chemical behavior. They all will form similar types of bonds with similar atoms. And then, so those are arranged going up in mass as you go down, and then he went up in mass as you go across as well. So that was Mendeleev's idea of organization. We now have a much better idea, but it turns out when you look at those, each element is defined by the number of protons in the nucleus. So hydrogen, the first one, has 1 proton in the nucleus. Helium, go across that top row, the last one in the top row, the second one as well, has 2 protons in the nucleus. Go down to the next row, lithium has 3 protons, beryllium 4, boron 5, carbon 6, and so on. So the number of protons in the nucleus is what sets which element it is. And which element it is describes its behavior, its chemical behavior. So protons is really important. Now we have in atoms not just protons. A couple weeks ago for Flip Friday you had the question, or was it just a week ago, about what was in an atom, and it was not just protons. What else is in an atom?
Protons,
neutrons, and electrons.
Quarks.
Protons and neutrons are comprised of quarks. Specifically, a proton is an up-up-down, and a neutron is an up-down-down. But for this level of class, we're not going to worry about the quarks. And so we have protons, neutrons, and electrons. Neutrons are in the nucleus with the protons, and the neutrons make virtually no difference for an atom. We call atoms that have the same number of protons but different numbers of neutrons isotopes of the same element. Isotopes of the same element because they're different, but they have the same chemical properties. Isotopes are used for things like determining if you have synthetic testosterone. Let's say that you are a bicycle racer. Your name happens to be something like, Floyd Landis. And I think he was one of the people who got busted, right? Wasn't he? Anyway, when they accuse you of having somebody else's testosterone, it's actually not that Labor donated testosterone and I took his testosterone. They have synthetic testosterone that's made from soybeans, basically. And soybeans are grown in a part of the world where the isotopic abundance of carbon-13 and carbon-12 is slightly different than most of the other food people eat. And so what they actually did to determine if it was his own testosterone or if it was synthetically made was they measured the ratio of carbon-12 to carbon-13 in that testosterone and compared it to the ratio found in most food people eat. Now, of course, I say, wait a minute. I'm a vegetarian. I get a lot of my protein from soy. Would I fail their testosterone test just because I have a different ratio? I don't know. They'd probably test the rest of the things in my body, and if the rest of things matched testosterone, I'd probably pass, right? But that was actually their test. It was an elevated amount of testosterone, and then they tested the testosterone to see if it had the right isotopic ratios, the right number of neutrons. Okay, so electrons then are orbiting the nucleus. What can you tell me about the electrons orbiting the nucleus according to our best knowledge?
You can see how many of them are by the charge.
Okay, we can determine how many there are by the charge. A neutral atom will have the same number of electrons as it has protons. If you have a +1 charge, that means you're missing an electron. If you have a -1 charge, you have an extra one. What do you say?
I would say that there's a certain amount on each energy ring.
Okay, certain amount in each energy ring. Now, we haven't talked about this, and we're not going to talk about it. It's a little higher level physics for this class. But there's only a certain number of electrons you can have in each energy state. So that's good information, advanced information. What I'm looking for is positions. What can you tell me about the positions of the electrons?
They're on the outside of, they're not like, they're outward of the protons and neutrons.
Outward of the protons and neutrons of the nucleus.
Position in relation to what?
To the atom, to the nucleus.
No.
Yeah. The answer is really nothing. Right? Our current understanding is we don't know what they're doing or where they are. We can only calculate where they're likely to be found.
So we don't know whether they're like moving, or are you just saying we don't know how they're moving?
One could be potentially stopped for all we know. We know that they have angular momenta, and if they have angular momenta, that usually means they're moving, but how they're moving, don't know, and it gets very confusing. So basically, we don't know. In fact, there are two approaches to quantum mechanics, and one of them is defined by, okay, we have no idea what the electrons are doing, so we're not going to worry about what they're doing. And let's just look at the values of their energies and angular momenta and ignore the things that we don't know. Okay, so, all right, here's where I had changed it up. Absorption and emission. Last week for Flip Friday, we did a little work with absorption and emission with the little, have light that you shine into the hydrogen atom and see what happens. Well, absorption occurs when you have light that comes in and the energy exactly matches the gap from a filled to an unfilled state. So over here we have a picture trying to illustrate the energy levels. The ground state is the lowest possible energy state. We call the lowest possible energy state the ground state. And for a hydrogen atom, that ground state is minus 13.6 eV. EV stands for electron volt. It's a unit of energy. That's all we need to worry about. It's a unit of energy. So the ground state is minus 13.6 electron volts. If you can take an electron and raise it up to 0 electron volts. Oops, didn't mean to cross that out. I meant to underline it. I missed again. Apparently I'm not good at aiming. 0 electron volts, then the electron will be free to leave. So if an electron is in the n equals 1 state of a hydrogen atom, its ionization energy, the energy necessary to pluck an electron off, is that 13.6 electron volts. So if you have a photon, which is the name for a particle of light, that comes in and the electron's in n equals 1, if it's 13.6 electron volts or greater, it'll be absorbed and the electron leaves. If it's less than 13.6, then its energy has to exactly match the gap between two energy states. So only photons with specific energies can be absorbed. And likewise, if I have an electron that's in an excited state, say the electron's hanging out here in n equals 4, it can fall down to a lower energy state. But it has to fall to exactly an energy state that exists. Kind of like my example where I talked about putting shoes in a closet. The shoes aren't going to fall down to halfway between the first and second shelves. They're going to fall down until they hit the bottom, and that's where they're going to end. So the electron, likewise, can't fall to some intermediate state. It has to fall to exactly one of your existing states. So absorption is light comes in, has energy exactly equal to a gap between a state an electron is in and a state where the electron can go to. That energy is absorbed by the electron. Energy can't be created or destroyed. The electron jumps to a higher energy. Emission is exactly the reverse of that. Emission occurs when you have, I thought I had it on this, it's coming after this. Emission occurs when you have an electron that's in an excited state, higher than the ground state, that falls down to a lower state and gives off a photon of light with an energy exactly equal to the gap again. The Bohr model predicts that the energy levels are given by this equation. Minus 2.18 times 10 to the minus 18 joules over n squared. Minus 2.18 times 10 to the minus 18 joules is that minus 13.6 electron volts. Right? They're just different units of energy. And so the energy for the hydrogen atoms is just this energy minus 13.6 electron volts divided by n squared, where n is an integer. N is telling us which energy level the electron is in. So if n is 1, you're in the ground state. N equals 2, that's the second state or the first excited one, and so on. So this better be my picture that shows photons falling, yeah. So here we have the energy spectrum for hydrogen atoms. Now, a little history. Cody, a little history. The Balmer series was the first one observed. And the reason is real simple. Look at my picture here of the electron transitions for hydrogen atom. What do you notice about the colors of the arrows? These ones here are colors in the visible spectrum. All the rest of them are all the same color of red. They chose red just to choose a random color because all of these here, the Lyman series, the Paschen series, the Brackett series, if you go up higher, the Funt and so on, those are all not visible to the human eye. And so the first ones that were discovered were the ones you can see with your eye. And then later on, they developed detectors that allowed them to see ultraviolet light, such as you have from the Lyman series, or infrared light like you have for the Paschen and Brackett and Funt series. So it's simply what we could detect is why the Balmer was found first. Now, the Balmer series gets its name because a school teacher noticed a mathematical relationship where 1 over lambda, who knows what lambda stands for? Wavelength. 1 over wavelength is equal to a constant called the Rydberg constant times 1 over n squared minus, or no, it's 1 over 2 squared. 1 over 2 squared minus 1 over n squared, where n is anything bigger than 2. I better rewrite that so you can read the whole thing. Balmer discovered that equation predicted all of the Balmer series lines, all of the colors. Didn't have a reason for it. It was just an equation that worked. And having that equation that worked, of course, gets you some fame. And then when the Lyman series was discovered, it was also discovered that if you change this from a 1 over 2 squared to a 1 over 1 squared, that would give you the wavelengths for the Lyman series. The Paschen series, if you change that from 1 over 2 squared to 1 over 3 squared, it'd give you the Paschen series. And of course, the Brackett series is 1 over 4 squared, the Funt series 1 over 5 squared. And so this equation really explains all of the emission lines given off by the hydrogen atom. Why does it explain that? Well, now that we understand things more and we have the Bohr model came after, this equation here says the energies are proportional to 1 over n squared. And since you have to have a photon going from one energy level to another energy level, then the difference in energy has to be proportional to 1 over the n squared you started with minus 1 over the n squared you ended with. And so that's exactly why this equation that Balmer found just from looking at data is correct. So if you have a bigger change in energy, you're going to have more energy in your photon. Now, we have to tie together a bunch of things about optics to make good sense out of this. So let's answer this question and then get on to good things about optics. Which model or models? This one, you have multiple possible answers. So if you think it's all four, you type in A, B, C, D and hit enter. If you think it's just A, you would hit A and then enter. But you have to hit enter for it to be recorded. Doing pretty good so far. Except for only 5 people have answered 6. Okay, that's everybody. Okay, so we had 3, 9, 6, 3. Well, that's kind of a mixed bag. The correct answers are the most popular answers. Rutherford's planetary model said that the electrons were orbiting in circles like planets orbit the sun. Of course, at that time, they already knew planets were doing elliptical orbits. But hey, c'est la vie. Bohr's quantum model stuck with the circular orbits. It just said that they were quantized, you had certain energies available. So those were the two that said that the electrons are doing circular orbits. The plum pudding model just said the electrons were sitting there. And the standard model says, we don't know what they're doing. Okay, so light. Many things on light that I hope to go quickly through. Why study light? Because it's what we get our information for astronomy about. If you don't understand how light works, then everything I say in class is believe me. Right? But if you understand how the light is interpreted, what it means, then there can be some clarity and understanding. And you won't have to nod your head like that, Kendrick. Okay, so light is typified by a few important things. One of the very important things is the wavelength. We already knew, people answered, lambda is the wavelength. Wavelength is the distance for a wave to repeat. So you can think of an ocean wave. Now, you see an ocean wave, you see something like this. You can't define a wavelength for that. But when you have another one, then the distance between them, you can say, aha, there's the wavelength. What's the difference in a normal ocean wave and a tsunami, or harbor wave as tsunami actually means? And scientists will get angry at you if you call it a tidal wave, because it has nothing to do with tides. What?
It's huge.
Okay, the wavelength for a tidal wave, which, like I said, scientists get angry at you, so call it tsunami. True story. I was in Japan watching sumo wrestling on the English broadcast because my Japanese is pretty crappy. I tell my son not to use that word. And the announcer says, we have a tsunami warning. And I was like, cool. Of course, I was in scuba. I was nowhere close to the ocean, so it wouldn't affect me. But then he says to his partner, now, what is a tsunami? And comes up with something really stupid. I'm like, dude, you're in Japan. You've got to know what tsunami was. And I wrote something on a sumo mailing list, and it turned out that he had been told, there's a tsunami warning, don't mention it on the air. And so he was trying to cover for having already mentioned it by trying to obfuscate what it means, hoping that the Americans, people listening to the English broadcast, wouldn't know. Okay, so a tsunami has a very long wavelength. That's what you said, right, Lauren Lee?
I said that it was very tall.
Very tall. Tsunamis going through the ocean are not very tall. Tsunamis going through the ocean might be 3 to 6 inches tall. Now, if it hits your boat, you're going to get a jolt because what you have is very rapidly moving water with a wavelength that's kilometers long. And so when it hits you, you were here stationary with the water, and all of a sudden all the water is moving at a constant speed after the wave passes. Not a big deal for the most part, just that jolt. But when you get into shallow water, then all of the energy of the wave, it slows down in shallow water. And because it slows, by the way, a tsunami is a shallow water wave traveling through the ocean. And immediately you should say, wait, shallow water, ocean? Right? Oceans are deep. But we define shallow as less than the wavelength of the wave. So they're really long wavelength waves, so the water is shallow compared to the wavelength. When they get into truly shallow water, coastal waters, then the wave slows way down. Its energy goes, instead of the water traveling like this, it goes higher and higher and higher. And so that's where you get tsunami, meaning harbor wave, because you don't really see it until it gets to the harbor. The water gets shallow and the waves get tall in the harbor. So you're looking out there in the ocean, you don't see anything, and all of a sudden it just rises up when it gets to the harbor. Good to know, right? Yeah, well, yes, I do think it's important. Okay, so the wavelength, the distance between the crests of waves. We also talk about things like the frequency, the amplitude, the wave speed. So the wave speed, we use V for the wave speed. I know that looks like a nu, but it's a V. C we use for the specific speed of light in vacuum. So the speed at which light is traveling through the virtual vacuum of space, we call that C. And C has a very exact number. C is equal to 299792458 meters per second. It's a fixed number. It's what? Yeah, it's constant, it's fixed. And if you do an experiment that suggests C is different, you actually have done an experiment to change the length of a meter. The C is the constant, and the length of the meter would be the thing that varies. Which is because it's only, 8 digits or something? I didn't count them, but 3, 6, 9. Yeah, it's only 9 numbers.
It's like memorizing a phone number.
Yeah.
And he's been doing it for like the past 25 years.
Not that long. But I did have a full head of nice brown hair when I started.
Well, you have been studying science for at least 45
Your hair used to be brown? Looks a lot darker.
45 years.
No, really, it doesn't look...
When I was in Japan, my friend described it as blonde because, Scandinavian, it started lighter and got darker and darker and darker over time.
Could you scroll down to that constant one more time for me?
Yes, I can. Okay, so we have the wavelength relates to the wave speed. Oh, wait, no, that is a nu. I should have looked at it more carefully. That is supposed to be a nu. Nu is the Greek letter that we use for frequency. And I should have paid attention. Yeah, because otherwise we'd have a problem with that equation.
For velocity.
Yeah, wavelength times velocity wouldn't make sense, would it? Wavelength times frequency is the wave speed. For you guys, you probably should be more comfortable just writing it like this. Frequency times wavelength is equal to the wave speed, and I'll put C for the speed of light. Because that's what that equation is. Frequency is measured in cycles per second, also known as a hertz. So we have the symbol Hz, stands for hertz, like I guess the car rental, or the scholarship offer you can see on the bulletin board out there if you're thinking of going to graduate school in science. And so we measure a wave. You can either talk about its wavelength or its frequency because of this relationship. If you know one, you know the other. When we talk about visible light, we usually talk about its wavelength. When we talk about radio waves, we usually talk about its frequency. Frequency is how many times per second something repeats. It's very closely related to period. We've talked about the period of an orbit. What's the period of the Earth's orbit around the sun? 365.2422 days, or 1 year. Right. So period is the time it takes to do a complete cycle. And so Frequency is cycles per time and period is time per cycle. See a quick relationship between those two?
Oh, yeah.
What is it? They're opposite. And so the period is just 1 divided by the frequency. So if you know one, you know the other. So once again, if you know wavelength, you know frequency. If you know frequency, you know period. They're all going to give us the same information. Now the particle of light has been proposed off and on by different physicists throughout time, but the photon really gets its energy from Albert Einstein. Now, I say it comes from Albert Einstein. Max Planck is the person who said, Caleb, you got to give it the program here, man. Thank you.
Is that better?
Yes. Max Planck was the person who said, if light comes in particles of energy, then I can explain black body radiation, something we're going to see in just a moment. But he said if. And then Einstein, he was the true believer. He was like, it is. Light is a particle. It comes in particles with energies of HF. And he proposed an experiment that people could do that would test to see if light was behaving like a particle or like a wave. Now, we've just been talking about light as a wave, right? We talked about its frequency and its wavelength. Those are things that waves have. A baseball doesn't have a wavelength, does it? A true physicist would say, sure, it's just way too small for you to discern. But most of us would say, no, baseball doesn't have a wavelength. It's a particle. It's, a BB doesn't have a wavelength. But science says that particles have both of those natures, and that light has both of the natures. Light can behave both as a wave and as a particle. And we have experiments to back that up. But to me, that illustrates really a misunderstanding that we must not know everything there is to know about nature because we have these two distinctly different behaviors, and we say light can behave as a wave or light can behave as a particle, and anytime you check, it'll be one or the other. And we have no explanation why, except for things like, you have 4 blind men that come and they feel an elephant, and one feels the tail and says, oh, it's like a snake, and one feels the leg and says, oh, it's like a tree. You guys heard that, right? Mm-hmm. That's the best explanation we have, but that means, we're not seeing the whole picture. So the energy of these particles of light, the photon, is Planck's constant. Planck is spelled Planck. But he's he's a German dude, and his name is pronounced Planck.
It's near the formula.
What was that? I just call the formula the equation for the energy of a photon. It was initially Planck proposed E equals HF, which is what this is. Remember that nu means F, so that's H times frequency. And H is the self-named Planck's constant. It's just a number. 6.626 times 10 to the minus 34 joule seconds, something like that. So we can take that constant and multiply it by the frequency. It's got to be joule seconds because you multiply it by frequency, that's 1 over seconds or hertz, and you get units of joules. Or using the fact that frequency is the speed divided by wavelength, you can also write it like this. So on Friday last week, people said, I see this equation in the book and this one here elsewhere. Which one's correct? They're both the same equation, just using the substitution that F times wavelength is equal to C. And remember, this nu is frequency. So the energy of the photons, the energy of the particle of light, is proportional to the frequency. Higher frequencies, higher energy for the photons. And so in just a minute, when we look at the spectra, we will get a better feel for that. Now light, when I was a kid, grade school, like 2nd grade, Miss Burchell got these prisms. And when we finished our assignments early, we could play with the prisms. And most of my classmates would take them out and look at the light coming from the sky and say, ooh, pretty colors, like you see there. I put them up next to my head and walked around and bumped into things thinking, oh, everything's upside down. This is the coolest thing ever. Well, prisms can be used to separate light into its constituent colors. So can what we call a diffraction gradient, and that's what these are. Please don't write on these, and please do give them back to me again in class. But if you put these on, also don't write nerd 4 eyes on them.
Does that happen?
Please tell me.
Tell me, does that happen, Cody?
Yes, it does.
I was reading the ones I was giving Cody. And then when I get them back, I'll just blame him. Okay, so you put these on, and you look at the lights, and what do you see?
Well, I see
Rainbow.
lights, but I see the spectrum.
Look at a light like completely across the classroom. What colors do you see from that light?
Orange and green.
Red, purple,
Purple.
it's kind of orange.
Okay, if you choose one that's far enough, I'm choosing the one in the very back corner. I see a layer of red, I see a very faint yellow, then I see a green, then I see kind of like an aqua color, and then I see a blue.
Yeah.
I don't see that one. These lights are fluorescent lights. The fluorescent lights are actually putting out those discrete colors. There's only certain colors that are put out. But when you look at them without the glasses, they look white. It's because our brains only can recognize 3 different things. And we have 3 cones, one that's most sensitive in red, one that's most sensitive in green, and one that's most sensitive in blue. And because of that, we say we have 3 primary colors of light, red, green, and blue. And everything we see for color is based on how much of the red cones are activated, how much of the green cones are activated, and how much of the red, green, and blue cones are activated. So these lights here, they just put in different colors to try to get even activation of those cones, and they trick us into thinking they're white. Now white, you might have heard, white is the presence of all color. White is a combination of colors. Now, the reason we got these out is so we can see that light is made up of individual colors. And then we're going to turn on some pretty lights here. So let's turn off everything. And I got a...
The light from outside looks like a gradient, just a flat gradient.
By the way, if you're up here looking into that projector, it's pretty amazing.
I wanted to see.
But I'm muting it. Okay, so I've muted that. Oh, crud. Gotta turn these off too. We want to get this place as dark as we can. And I'm going to turn on this light here.
Those are amazing. They look so cool.
So this light right here,
The existence of boss.
I'm going to warm it up. I think I have it on. Yeah, I might even not.
Uh-oh.
Okay. So there it's giving off just a little bit of light. Now, what color does that light look like? I mean, like, how would you interpret it?
Orange.
Okay, orange. Now, when you look out these glasses, is it bright enough for you to see the lights that are on the sides?
I can.
Okay, what do you see when you look at those lights on the side?
I see green and red.
Green and red. And are they distinct?
There's mostly red, and it kind of just fades into a little bit of green, but there's nothing much more than that.
Okay.
They're not quite distinct.
Now, I'm going to heat it up some more. When I heat it up, you should notice a few things. What's the first thing you noticed? It got brighter. Okay, so it got brighter, which meant that it was giving off more energy. And I'll take heat. Now, if you look at the colors off to the side, those should be clear now. What do you see for those colors? And the blue is very faint, right?
Yeah.
Yes.
Now I'm going to heat it up some more.
Whoa.
What happened to the color?
Brighter.
It got brighter and the color became whiter. Okay. The color became whiter. It's still not white. It's still got a yellowish tinge to it. If you look at the colors off to the side, you see now you're getting more blue into it.
Yeah.
Now if I heat it up even some more, what's happening? Yeah, now it's starting to see purple. You're getting more into that purple, and of course it's getting brighter. Heat up as hot as I can. That's about as close to white as I can. Hopefully I don't burn the filament because this is made so I can actually make it so I'm putting in more than it's supposed to have. Looks pretty white now, and you see the entire colors of the rainbow off to the side. So what we see here is when I make it hotter, it gives off more light, and the colors present shift toward more blue when I make it hotter. Now we're going to see in just a few moments the actual mathematical equations, but here we can see it in a practical sense. This is called black body radiation. Black body because black is the ideal color for something to absorb or radiate light. And so something that's black is going to be very efficient. As you had on your Flip Friday pre-class worksheet, the human body is very close to an ideal black body. It's about 97% efficient. And so I didn't worry about the 97% and just use that. Okay, now I'm going to turn this off and turn this on. Now what color is that filament? Or it's actually not filament, but what color is that line in the middle? Magenta. Magenta being one of the primary pigments or secondary colors of light. A fuchsia, is that what you said?
Yes.
Excellent. Excellent call. This is, well, I believe it's hydrogen. I believe it's hydrogen. It said hydrogen, and I didn't check to see if it was helium or not, because it somehow seems to me that it might be helium. But what's important is what do you see when you look off to the sides?
There's some distinct lines.
There are distinct lines. Why? Because this is a gas, and it's producing the emission spectrum. Well, how is it producing emission spectrum, you ask? We have electrons that are flying up and down through there, colliding with the hydrogen atoms. And when they do, they will excite electrons, transfer energy to electrons, and make them go to higher energy levels. Well, what does an electron naturally do when it's in a higher energy level?
Go back down.
It falls back down. And so when it falls back down, it's giving off the light. And if you look at the distinct colors, you see it looks like there's a violet, a blue, some goofiness in the greens and yellows and reds. I think that's due to water or impure gas. Then you've got the red.
Do you think maybe the goofiness is because of the 2 parts in the top and bottom not being pure?
I think it's because the gas itself is not pure. That it's had some leakage and gotten some water vapor in there or something. But here we see very distinct different colors as was observed with that hydrogen spectrum that led to the Balmer series. And it was those distinct colors that was one of the primary reasons why Bohr knew that Rutherford's model wasn't correct. And so this here is a discrete spectrum that comes from electrons falling from higher energy levels to lower energy levels. This here was a continuous spectrum that was caused by something being hot. So we have 2 different ways that we produce light, the continuous spectrum or the discrete spectrum. It depends on what the source is. Any questions about this?
I have a comment.
Comment away.
You should look at cell phones.
I should look at cell phone. Well, I've got
Really weird.
my tablet right here. You should see the distinct colors again, right? Because you only make 3 colors, right? Your cell phone's only making 3 colors.
It feels like there's 4 screens.
Yeah, because you're seeing the different colors shifted by different amounts. And so yes, it's quite cool. All right, gonna turn the lights back on, so be ready for the lights. Remember, I do want these glasses back.
Do you have an extra copy of your
No. I love these glasses though.
Where can you buy these?
These here I bought from a science store, but they're actually made for children's birthday parties. That's why they have these pretty.
That's so cool.
Scientists actually use gratings that are only done in one direction. These are done in 2 directions to make it so it's prettier for the kids. And all I care is that we can separate the colors, so I'm happy with it. Well, I also care that it's cool, and it's cool. And my projector just, or not my projector, okay, let's get this started back up. I ignored my tablet too long and it got lonely. So lonely, you could cry. All right, back to it. Kendrick's helping me out, appreciate it. Kendra's just taking the ones he's taking home.
Taking them all, you know.
Okay, so we have this light can be broken up into its individual colors. So the sun, we see the sun is pretty much yellow. The last slide today, should life last so long, well, the next last slide, is the spectrum of the sun, so you can actually see what the different colors present are in the sun. Just set them up there. Appreciate it, man. So here is a spectrum. Spectrum is just showing the colors. Now, light is an electromagnetic wave. It's not the only kind of electromagnetic wave. Radio waves, actually radar is a microwave, I guess. Radio waves are some of the lower frequency or longer wavelength waves. Then we have microwave. The Greek letter mu stands for micro, and I didn't have space to write out all of microwave. Infrared, visible, ultraviolet, X-ray, and gamma. Now, something interesting. All of these are really just ultraviolet. The distinction for gamma rays means it's coming from the nucleus of an atom. X-ray means it's coming from electrons falling into closely bound states in an atom. So X-rays and gamma rays is really talking about what's producing them. And so they're all really ultraviolet, but those are typical ranges for them. And there is broad overlap between the X-rays and the gammas because the real distinction is the source. Now, the visible spectrum is what I want to focus on right now, and then a few ticks, we'll get to looking at the others. So the visible spectrum goes from about 750 nanometers for the longest wavelength of visible light, down to about 400 nanometers for the shortest wavelength of visible light. Now, you might all be just a little more clear than what I wrote and say, I am pretty sure that that violet goes off to the left past 4. There's not a distinct cutoff for the eyes. They just become less and less efficient as you move down there and as you move up to the top. So these numbers are not exact numbers. I choose 400 and 750 because 400 nanometers and 750 nanometers, if you convert those to frequencies, it's 4 times 10 to the 14th hertz and 7.5 times 10 to the 14th hertz. So 750 nanometers is 4 times 10 to the 14th hertz. And 400 nanometers is 7.5 times 10 to the 14th hertz. And that's why I choose those numbers, because I can keep the numbers straight for both frequency and wavelength. Yeah, I'm halfway through and I got 2 minutes. We'll clearly get to the end. A quick look at radio waves, microwaves, infrared. We see different kinds of details in astronomy using the different wavelength ranges. So the visible range, the obvious one to us, is not the only useful one. So with radio waves, you can see very long things. With radio waves, you can see things like where neutral hydrogen gas is in the universe. You can map it out using radio waves. If you're looking for infrared, infrared to you and me is very useful. You guys have heard of night vision, right? Night vision is looking at the infrared radiation given off by something because it's hot. You are hot. You're giving off radiation. It's just not in the visible range. It's in the infrared range. Ultraviolet, X-ray, gamma rays, those allow us to see some of the more energetic things going on in the universe. So you can see the pictures here are illustrating some of the cool things you see with those different ranges. Okay, this will be our last clicker question, for sure, faux show. You can answer starting now. What is the approximate wavelength range for visible light?
No.
Notice the top two have units of nm and the lower two have units of mm.
Yeah.
What does that mean? Yeah.
That was, I think, the first day I said you need to memorize these prefixes. Okay, I'm going to move on. Okay, the correct answer here, we had 9 that said this, 1 that said this, and according to Alina, that's the answer. Only according to Alina, because she's correct, of course. Right? Right. Okay, I am going to end with 2 quick slides, one showing, I don't know where they are. This is just temperatures. By the way, I was a little bit off, but pretty close on absolute zero in Fahrenheit. It's 459.7 or something like that. Where's my Wien's law and Stefan Boltzmann, which actually are on the same, the sun's a black body. They're on the same slide, which is coming up. This one here, well, that picture will be reproduced on the next slide, which has the Wien's law is a law that says the hotter the body is, the more strongly it will emit at shorter wavelengths. So when we were looking at this, when I made it hotter, we saw more blue. That's a shorter wavelength. That's illustrating Wien's law. The Stefan Boltzmann law says the luminosity, how much light is given off, depends on the temperature. The hotter it is, the more light it gives off. And the actual equations for those laws, this here is Wien's law. The temperature is equal to 2.9 million kelvins times nanometers divided by the peak wavelength, the color that is strongest in the emission. And finally, the Stefan Boltzmann law, the luminosity, L is the luminosity here, is equal to a constant, sigma, the Stefan Boltzmann constant, multiplied by temperature raised to the 4th power. Notice that's a very strong function of temperature. If you double the temperature, 2 to the 4th power is 16. So you double the temperature and the light that's given off is 16 times greater. So that's pretty extensive. And I think this slide here had, nope. Okay, well, let's stop here because it's 2:22, which means it's past time to stop.